All right. Uh, Sorry for power going out at the building. Still totally unsure what's going on. Somebody got trapped on the elevator, so at least that wasn't y'all. I hope none of y'all got trapped in the elevator. Anyway, at first I was having an issue. I don't know what this looks like exactly. Apologies if it is in fact a big black screen that says iPad and then my face is small right here. I'm using my iPad to draw on. So in a moment, instead of being iPad 504, it'll have an actual whiteboard that I'm drawing on, hopefully. There was a moment where my iPad's sitting next to me because it has to be signed into the meeting. I could not get it to stop also playing my audio, like even turning the volume all the way down, it wouldn't let me turn it to zero. Um, which meant if you've ever seen like a speech jammer before, that's something that's playing your audio back at you with just a very slight delay, and that's meant to just confuse you and make it harder to talk. I had that going on, and I thought that I would have to deal with that the whole recording. But I got it to stop. I signed out of audio on my iPad, so whatever. Anyways, so with the lesson today, I think I'm going to make this into two separate videos so that hopefully one of them can start uploading and maybe available to watch while I'm recording the other one and waiting for the other one to upload. These videos take a little bit of time to upload to things. Um, so first video, I'm going to start over a little bit with linear models that we talked about on Friday, and then I'm also going to get into exponential models. So yes, today we are doing linear models. I have a graphing calculator on my computer through some, I don't think it's, I don't think it's actually sketchy, but I guess you can judge whenever I go there. Uh, but I have access to some website, I guess. I don't know. So we can look at my computer that shows a virtual graphing calculator that hopefully y'all can see what I'm doing on there and follow along with that. Um, Either way, what is a linear model? So a linear model is specifically, if we remember, it is, oh, hopefully this looks nice. Um, why is it green? There we go. Okay. A linear model is a linear function with all of its context. Essentially, if you remember anything from functions and modeling, then models, as you can probably tell from the name of the class, are a lot of what you deal with. Um, so this is part of the buildup to where business calculus is trying to actually go. Business calculus is trying to do calculus or calculus for business and life sciences. Is trying to do calculus on real life scenarios, things that people are practically working with. So it is not enough for us to merely be working with an abstract function, as I'm used to working with. This is why we don't whisper to ourselves. Found it. Okay. It is not good enough for us just be handed a function and work with it in some abstract sense without any context. Because for the purposes of this course, we need to be able to have a situation, a real life situation, model that with a function, and then do calculus work on that. So in that sense, in order to know what do I mean by context, we have a few things that we want to make sure that we include. So for one, we want to include input, units, and description. So something like if we're at the gas tank or at the gas pump, then our input units would be gallons, but the description would be gasoline purchased at the gas station. So we would say gallons of gallons is a unit, but we need to describe the situation to give more context. Gallons of gasoline. That is still kind of a unit, so the description really needs as much context as we can give it being purchased. And there's some situation where maybe even clarify in an individual purchase at a specific gas station. The more description you give it, honestly, the better off you are. I struggle with this a lot because I'm used to giving a minimal amount of words, right? We do our homework. It's very often that we try and write as little down as possible so we can be done with it as soon as we possibly can. But that is not descriptive. Here, we are trying to be as descriptive as possible. We're trying to give as much context as possible. So if you told me gallons of gasoline being purchased in an individual purchase, or being bought in a single purchase at specific gas station on a specific date, that overkill? Yeah, kind of a little bit, but really that's all in a way kind of relevant, right? The price of gasoline can fluctuate daily and definitely fluctuate by where you're at. So in a sense, as many details as physically possible sometimes are important. However, at a certain point, it is overkill. So we're most of the part, something like gallons of gasoline being purchased is a reasonable area of what we aim for. So we want input units and their description, but we also want, you've guessed it, output units and their description. So, for instance, of what we were modeling was you going to the gas station to buy gasoline, then your input units and description would be gallons of gasoline being purchased, but your output units may be dollars owed to credit card company. And maybe you're paying for it with a debit card, in which case you would be dollars spent, dollars reduced from your taken from your bank account, whichever way that you really want to articulate that. I'm not incredibly picky, especially for scenarios like this where there's kinds of a few different ways to go about it. But a specific situation will call for a specific way of giving these descriptions, specific circumstances. And I realize that you was a horrible you. Okay. Um, units. Okay. Um, and you will also see sometimes, I think, the way that we wrote it in class, there was like a 7 or 6 individual things. The first one was accurate and consistent function notation, which is essentially saying nothing. That's just saying you write everything down consistently and well, which I think is just automatically assumed out of every part of life. It'd be like if I told you a good writer is a writer who writes well and also with good quality. And it's like there's redundancy in that, right? So I'm not going to write that down here, but as a general guideline, be consistent and use accurate function notation. But additionally, a complete linear model includes input and output units and description, but also, most importantly, maybe not most importantly, because without context, I don't know what we're looking at, but very importantly still is a function with coefficients that is numbers rounded to at least 3 decimal places of accuracy. My wording may be off there. Maybe it should just be a function with coefficients rounded to at least 3 decimal places, or a function with coefficients with at least 3 decimal places of accuracy. So my wording is not exactly grammatically correct there, but we know what I'm saying. A function with at least 3 decimal places of accuracy, right? So if my function was supposed to be gas spent at the pump, then my input is G instead of X. I'm calling it G. It's just the names we give our variables. Then this might be 3.11 G. And then imagine your credit card company charged you $1 for using it in an individual purchase. Then, because we made a purchase, we would also owe them an additional dollar for making this purchase. And then we may name our function C as our output. So this might be our function C of G is equal to 3.11 G plus 1. Again, our inputs are very clear and consistent. Our input here is G, so we would write G in the function. An example of not being consistent with our function notation would be if instead this was X that we wrote here, but I still had this G right here. So it's as if right here I'd be telling you plug in a value G, but then in the function I wrote X. That would be wrong. That would be not consistent function notation. Now you could have C of X and then have X here. That's fine, because then you're just naming that input variable X. You are perfectly allowed to do that. You're allowed to name it whatever you want, but you're supposed to be consistent with that name. X is typically what we use for input variables, but whenever you clarify and specify, I am inputting this number G, this variable G is the variable, is my input, then you need to use G in the function. And why did I choose G as a number or as the variable? Well, G is short for gasoline, and our input are gallons of gasoline. Maybe G is short for gallons, however you want to write it. And then C is short for cost or credit card, whatever way you really want to think about it. Realistically, the names you kind of want to, what's the word, give some kind of relevance. I want to say incite. I don't know, resemble the words that the inputs and the outputs. So sometimes it's just going to be the first letter of whatever input you're taking, and the first letter of whatever output you're taking are going to correspond to what you name the function and then what you name the input. But realistically, they're arbitrary. That's a variable means. Anyway, a linear model is all of these things. However, specifically, a linear model is one whose function is linear. That is, the function is a line. So this whiteboard won't let me scroll. That's very interesting. I press this. Okay. So specifically, our linear models are function models where that function is a line. So everything that I've said about linear models is true for models in general. It's just the example that we use here would be different. A complete model is one with 1 and 2 still there, as well as 3, because I didn't even specify in 3 we were supposed to be a linear function. Now, for a complete linear model, that is going to be linear. But this is actually generally true. If I erase linear, this is also something to write down in general, something to keep as true in general. And throughout the different models that we will encounter, we're going to kind of show what details do we need to know about the model? How do we find these values from what we're given, and how can we make sense of what's happening there? Excuse me. So when we think about it, a line, right, is a straight line between 2 points. And you may remember the equation of a line is y equals mx plus b. So this gives us a straight line. And in order to find out a line, I believe we are able to just do, um, I think the equation, I don't remember it. There's another form of writing the linear equation that sometimes if we just have 2 points, it helps us find that. That's not relevant for this class because we're going to be modeling real life scenarios. So instead of oftentimes figuring out exactly, instead of taking 2 points and finding the line that runs between them, what we are going to do more often is taking a set of values, a collection of data, and assigning a function to that, finding a function that is the best fit function for that, which is something again from functions and modeling, but is going to be something that we use and do in this class as well. So at this point in time, imagine that someone gives us a table of data and says, give me a linear model describing the situation. And you're like, what do you mean you give a bunch of data? I mean, imagine we are given this table with X and Y values, and we plug in 5 and get 50, 4 and get 47. I can't write, it's supposed to be 6. 6, get 47, 7 gives 44, 8 gives 41, 9 gives 38, and 10 gives 35. Now, it so happens that these points in this specific combination, or this specific list, um, does make a perfect line. That is, if you graphed all of these points in the plane, you would get a really nice line. Why? Because this example is made up. It's not real. It's not based on real information or data. This is just something that someone has picked that makes a nice line. How can we find the line that runs through all of these points? Well, if you are a great mathy person, I don't mean that like you're a great person because you're mathy, but if you are a person who is great at being mathy is what I mean. It's not a value call. I'm saying a skill familiarity thing. Then you may automatically say, okay, well, if I have this equation y equals mx plus b, then the only things that I need to figure out are m, the slope, and b, which is the y-intercept. Well, the slope is rise over run. The change in y over the change in x, which means I can take maybe this is x1 and this is x2, this is y1 and this is y2, and say that 47 minus 50 over 6 minus 5 should be my slope. 47 minus 50 is -3. 6 minus 5 is 1. So my slope is -3. And then b should be the y-intercept. And well, blah, 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 you do math from there and you figure out what b is. For our sake, we're not typically really going to take that approach. We can, and I probably will in class tomorrow show an example of how we can do that. But we are given our graphing calculators for a reason. And oftentimes the data that we actually work with, that you often do work with in the real world, instead of looking like a line like this, what was that? My iPad acted like I could change the page for a second, and now it's not letting me anymore. Anyway, so instead of acting like a nice line like this, in the real world, our points are not going to be so perfectly fit to a line, and they look pretty scattered like this. And we want to find, we can kind of tell that it looks like it's aligned, but nothing's really lining so perfectly to it. But I want to find the line that is the best fitting line for this data. Well, our graphing calculator is able to find the best fit line. So if I stop this and start, I think this, no, okay, great. Sorry. And there we go. Okay. This is very weird. This is just to get the graphing calculator working. Okay. Yeah, here we go. Here's the graphing calculator. Don't question this. So if we have our graphing calculator, I want to find the best fit function for a set of data that I have. Well, how can we enter data into a table? So before, what we have done before was a table, right? That's the graph. I hit second, table. Yes, okay, this is the table that we are used to seeing. There is another table that we can access where we input the X's and the Y's. And that is not a table, as we're going to call it anymore. It is a list. So remember, the table is where we put in X values and we get these Y value outputs that we use for doing the limits and that kind of stuff. The list is where we are given a list of points. So if you're given the information, you want a list. If you're finding values, you want the table. So where we're going to go is list. So I just edited this in order to, because I forgot what to do. So in order to access our list, we press the stat button right there. And then here we see a few options, and one of them is edit. We want to edit the list that is currently stored. So we press enter there. Okay. So, sorry, I'm trying to be on L1 and I pressed too many buttons. Okay, so in our first column right here, that is L1, we want to make our X values. So I'm going to plug in the X values, the inputs for that table that we had. And this was 5, 6, 7, 8, 9, and 10. And then we want to input the Y values in our second list. And those Y values are 50, 47, 44, 41, 38, 35, 35. Okay. Now we want to find the best fit function for that. So all things list related, we go to our stat button, and then we want to do calculus. And if we notice, the second option right here is calc. So we press the right arrow to go to the calc options. And we are doing what is called linear regression is the name for this thing that gives us the best fit function. We're doing linear, if I can. Okay, we're doing linear because we're trying to find the best fit line. If we wanted the best fit something else, we would do something else, but we want the best fit line. Okay, so here we make sure that this is correct. Our X inputs are the first list, L1. Our Y list is the second list, Y or L2. And then we're going to store this in a specific function. So if you are on a different calculator, I think like mine, which I'll show in class, when you go to this screen, it will not, whenever you press this button, it will not have all of these options. It will just say linear regression. In order to store this, instead of having this option that says store it right here, you're just going to do what I do right beside where it says it. So right here, it says store regression. It is trying to store the equation in a specific function. So we have to tell it which function we want to store the answer into. Well, our function is represented by a variable. So this button right here that is VARS, we press that. Well, output values functions are y variables. So we go there to the y variables and we want functions. So we press enter there. And this is the list of y1 all the way down. These are just the same as if we just press y equals at that top left button. These are those. So I press enter on y1 and boom, it puts in y1 down there. So now, because of the way that I type this, it will store this linear function, the best fit function, as the function y1. Now we go down, hover calculate, and hit enter, and it tells us our linear function. So it says it is of the form y equals ax plus b, where a is -3 and b is 65. So if we noticed before, I actually found that, well, the slope is constant. It's the same throughout. It is a really nice line. So the rise over run should be -3. And I could find that by hand. And I could have kept going and I would have gotten that the y-intercept had to have been 65. But this calculator did all this for us. It calculated the slope, it calculated the y-intercept. But something is really interesting. Not only did it find this for this really nice and perfect line, it will find the best fit line for functions that are not sitting on a line, right? Because if I just pick 2 points, there is a single line that runs between them. And if I pick a third point off that line, I can't get 3 points to all sit on the same line all the time. All it takes is 3 points for us to not be line by chance. You have to be careful with how you pick points once you go past 2. So in general, we will not be able to find a perfect line that goes through all the points, but our calculator can. Also, a program that I did in my undergrad can. But we don't use the program I made in my undergrad, we use this calculator. Okay, now again, if you're on an older calculator, that list will have not pulled up. It will not have said the button calculate. What would have happened is it will just say linear regression. Here, I'll use the iPad. It would have just said, I think it would look like this. You would type in this, and then once you hit like the option to do this, this would show on the screen, and then you would hit variables, y variables function, and hit y1, and it would put this right here, and then you just click enter again, and then it will do that, and then it will take you to the next screen. That is y equals m, or it's, what was it, ax plus b, where a is whatever and b is whatever. It was -3 and 65, I think. But the older calculators will still do this. This is just one of the moments where they look really different, but it's doing the exact same thing. Now, if we go back to, come on, cooperate. If we go back to our screen here and we go back to our calculator and we go to our functions, oh, there it is. It stored this best fit function as y. Now we can even graph it. The settings aren't right, but in theory, we could. Oh, let's go to window, and the y max is at 10. So let's do 100 instead. And I think it will show up on the graph. Yep, there we go. It was zoomed in too far, so we were just looking at like this square at the bottom. But yes, exactly. This will store our function in our calculator, and now we can do things with it. It found the best fit function, and it stored it in the calculator so we can work with it. Very good. So this is a little bit with our linear function. Now, there's two things that we can do. We found a function that models our situation. Let's say this was something like the cost of a house, or the S, like someone had someone come in every few years and give an estimate on what their house is worth. Now, they did this every year, but let's say that the value of the house, right? It's a continuous function. It's changing as on any given day. Your house may be worth something slightly different as the market's changing all throughout time. Now, hopefully, it's not decreasing. Sorry if it is, but that's the market. Who knows? The market's really good for selling houses right now. That's not relevant. Let's say this is an equation modeling the value of your house at a given year. Well, now we may want to find the value of your house on a year in the future. So maybe all of those values in the table were values that you knew were true and were already measured. Maybe these are years since 2008. 5 may have been 5 years since 2008, something like that. 10 is 10 years since 2008, 2018. But what if you want to find the value in a year after something that you have measured? What if we're looking for a value outside of the data given to us? This is what is called extrapolating. Extrapolating is finding values outside of the range that we were already given. So that would be if, because again, my function only went from 5 to 10. Extrapolating would be if I wanted to find the value at 15, because that is outside the data that I have been given. EXT and extrapolate, or EXTA, right? Extrapolate is like exterior, outside. It's outside the data given. So if we go to our calculator menu, I can go to my y variables again, and I want to know y of 15. Now, what I have just typed is telling the calculator, plug in 15 to this function. So what is the output when the input is 15? And it is 20. This would be extrapolation because I'm finding the output for a value outside of the range that I have been given. However, what if you want to find a value within the inputs that you've been given? So not necessarily just reading the table, right? Because it gave us a 5, 6, 7, 8, 9, 10. What if I wanted to see where I was halfway between the 5th year? So again, it didn't say what the value of my house was in the middle of the 5th year, but I can still plug 5.5 into my function and get an answer. This is called interpolating, interpolation. Extra means exterior. Intra means interior. So you're extrapolating when you're looking at data outside of the information you've been given. Intrapolating is when you're looking at data within the range that you've been given. So because 5.5 is in between 5 and 10, that's intrapolation. Because 15 is outside of the range 5 to 10, that's extrapolation. So again, I will write those things down. And we share content whiteboard. There we go. Extrapolation. is getting data from outputs outside of the range given. Interpolation is getting this is meant to be inputs, getting data from inputs outside of the range given. So our data that we get would be outputs. So getting outputs data from inputs outside of the range given. Interpolation is getting outputs from inputs within the range given. Within the range given. So again, if all of the input values were between 0 and 20, interpolation would be finding the value at some intermediate time there. Extrapolation would be if you went past 20 or before 0. So if you're going outside of the range, that's extrapolation. If you're staying within the range, it's interpolation. Okay. So that is all that I have that I want to talk about right now for linear models. And I'm going to post this and then start a video for exponential models. Goodbye. Takes a second to end this. Goodbye.